Okay, let's go over a couple of problems here. The first one is we have a carboxylic acid. I'm treating that with thionyl chloride, and then I'm reducing it with a version of lithium aluminum hydride. So if you notice over here, it's not LiAlH4, it's rather LiAlH and then OTBU3, which basically means that while lithium aluminum hydride delivers 4 hydrogens, or hydrides rather, this is going to deliver only 1 hydride. That's the only basic difference between the two. But it's a reduction reaction, nevertheless. So how do we go about it? Of course, you can perhaps see that the first step is the conversion of the acid into the acid chloride. So your product will look like, I'm going to draw the product just so that you can, follow along. And now we are supposed to reduce the R C double bond O Cl further down. And so it gives you, upon treatment with H minus, realize we're supposed to treat it only once. The hydride is going to attack, electrons are going to move on top of oxygen. You're going to end up with the benzene ring. Oxygen with negative, hydrogen came to its position, Cl still intact. Electrons come back, Cl leaves, and you end up with the corresponding aldehyde. Recall from class, if you would have treated this with lithium aluminum hydride, which is like a punch in the face amongst reducing agents, is the king of reducing agents, then this reaction wouldn't have stopped at RCOCl, or rather the aldehyde. It would have gone all the way to the primary alcohol. So in that case, your product would have been OH. So depending on the kind of reducing agent, if you have a moderate reducing agent, you can stop the reaction at the aldehyde stage. If, on the other hand, you have a strong reducing agent, in that case, you're going to go all the way to the alcohol stage. All right, the next question is, the student was asked to write a mechanism for the following reaction. So you have a ketone, which is being treated with ethylene glycol in presence of an acid, and you end up with the acetal. Which of the following intermediates would be the least likely to be found in the correct mechanism? So you have to think about how the reaction mechanism goes through and how you're going to write the mechanism. So of course, one way is to write down the complete mechanism. The reaction obviously would start with your activation of the carbonyl, because your nucleophile is a neutral nucleophile, so you must activate it first. So you will have the protonated carbonyl, so of course A is likely. And then you're going to show the reaction, the attack of the nucleophile, which is the alcohol in this case. So let's just take a step. You should have already gotten the answer based off what we have learned in class, but I still want to go step by step in case somebody doesn't have that yet. And so now you're going to generate a species that looks like oxygen with a hydrogen positive charge, OH, and it's then going to, water is going to, it can pick up the proton and release. So C also is likely. Notice what's going on here in D. D is the one where you have a negative charge, and what have I said about negative charge in presence of an acid? That never will happen. That never can hold true. Oxygen with 3 bonds, not going to happen, because your bond is going to be through the carbon, not through the oxygen. So D is the one which is the least likely to happen. Everything else is going to happen in that mechanism. All right, let's go forward. Choose the answer with the correct number of hemiacetal and acetals in the following structure. So you have been given a structure. You have to say what's an acetal, what's a hemiacetal. So let's just go carbon by carbon. If you notice, this particular one has an OH and has an OR. So there is one for the hemiacetal. If you go to the next one, it's only OH and H, so we don't worry about that. To the next one, you have essentially an OR, and then it's going to a carbon, so that's an ether. If you look at the other one, that also is an ether because it has an oxygen on one side and it has a carbon on the other. If you go over here, you would see that there is a ether on one side and there's a carbon on the other side. So there's basically only one hemiacetal that is present in this structure in the ring part. And if you consider this carbon over here, that has an OR and an OR, so that's your one acetal. Your choice B is the most appropriate answer. All right. Okay, the next question is, in addition to the expected ether, so the ether is given, a second isomeric product is formed based on the mechanism, information. What do you think would happen? This is pretty straightforward. You know that carbon is delta plus, bromine is delta minus, electrons are in resonance. This is going to attack, ta-da, and the Br is going to leave. You're going to end up with a C double bond O, and the alpha position should end up with your CH3. So that's the alpha alkylation that we've been talking about in chapter 23. All right, next question. Choose the order that has the following hydrogen atoms correctly arranged with respect to increasing acidity. Realize anytime you have electron withdrawing groups next to a carbon, that automatically means that it's going to be electron withdrawn, and that means that that particular hydrogen is going to be the most acidic. So the one where H1 is most acidic, so I have two choices. One is B, the other is D. Notice 3, which is connected to no electron withdrawing group, so that should be the least acidic, and that is your appropriate answer. All right. Okay. We have an IR here and some structures given, and you have to basically say which of the structures satisfies that IR. So a couple of things here. When you take a look, there's a 1700, and that should tell you that there's a carbonyl. Guess what? All of them have a carbonyl. But then there is also like a really broad peak, which starts around 2500, goes on around 3200 or so. So that's indicative of carboxylic acid. So carboxylic acid is present in A, C, and D. So B and E we can get rid of. We do not have anything at 1600, and we do expect, if A were the structure, then we do expect a 1600 double bond, and so that can be, you can remove that one as well. Now, the 2200, that tells you that it's a triple bond, but then there is also a 3300, and that is indicative of a terminal alkene as compared to an internal alkene, and so that means that your most appropriate choice will be structure D. All right, let's go forward. Okay, the next question basically has 3 different compounds. One is an alkane, another is an ether, the third is an alcohol, and it's asking that you have to correctly arrange them with respect to the increasing boiling point. So hopefully you can just recall from organic 1 that the alcohol is going to have the hydrogen bonding, and the ether is going to show polarity, and so the only thing that it will suffer of is dipole-dipole interactions. And the alkane is going to have only the van der Waals London forces. And since these are the weakest, you can perhaps see that this is going to have the least boiling point, followed by the dipole-dipole interaction, followed by the hydrogen bonding, and hence the boiling point also will be in that order. All right, so the question here is which one of the sequences below is the best synthesis of E3-hexene? So let's first just draw that on the side so we know what we are talking about. 1, 2, 3, 4, 5, 6. And we know that it is E because your high priority groups are across the double bond on opposite sides. That's why it's E. And so you can also call this a trans 3-hexene. You can call that a trans 3-hexene. So hopefully you can see, I mean, irrespective of how the reaction goes, hopefully you can see that the hydrogen with Lindlar's catalyst is going to be a bad idea because that always gives you a cis alkene. So you can just throw E out of the window. Let's go over each of these kind of, one by one so that we can take a look at what's going on in the reaction pathway. I have over here propyl lithium, and that can go through two reactions. It's a nucleophile as well as a base. If behaves like a nucleophile on the aldehyde, it's going to behave exactly like a Grignard reagent. We discussed this in organic 1 and then again in organic 2, but of course we focused more on the magnesium rather than the lithium. But you could write here CH2 negative MgBr and it would do the same thing. OH CH2, CH2, CH3. So you end up with, from an aldehyde, you end up with a secondary alcohol. And then I'm treating that with HBr. So that's going to give you a Br over here. And now I'm going to treat it with a bulky base. This is a bulky base. Now, when you run your elimination reactions with a bulky base, it's the Hoffman product, Hoffman elimination that's carried out, recall from organic 1 again. On the other hand, when you do it with a regular base, then you end up with a Zaitsev product. In this case, it doesn't quite matter because both of these positions are beta. They do have beta hydrogen, and it's not one over the other. Essentially, both of those systems are secondary systems, so more substituted or less substituted doesn't really matter. You're going to end up with a mixture of products that looks like a combination of these two compounds. So whether you choose to follow A or C, it's going to give you the same product. And since it's a mixture, I don't consider that best. So A and C can also be thrown out of the window. Now I have B and D. So the first step is, of course, going to be treatment with Br. So you end up with 5 carbons, and then we are going to add a methyl by treatment with sodium hydride and further it with methyl. So notice your triple bond is coming at location 1 and 2. So with trans conditions, which are sodium and liquid ammonia, you're going to end up with E2-hexene, and that's not what you want. You want E3-hexene. Let's see if item D gives you that. So when you add 2 carbons, you're going to add that on one side, and then you do the same thing on the other side, and with trans, looks like, yes, you will end up with a 3-hexene, E3-hexene, and so D is your most appropriate answer. Hope you were able to follow along. This is kind of like a mix of organic 1 and organic 2. So in that case, a very typical PCAT, MCAT type of a situation. All right, let's go forward. This stems from chapter on alcohols, and one of the methods that we discussed in formation of alcohols was through alkenes. Notice we learned 3 different methods. You can either do a hydration in presence of an acid, you can do hydroboration reaction, which is what these reaction conditions are, and the third one was the mercury reaction, which was also following the Markovnikov's rule. So in this case, since it's hydroboration, this is one of the 2 reactions that do not follow Markovnikov's rule, and that means that your OH should come to the least substituted site over here, and it should go to the least substituted site over here. So your product should look like an OH over here, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the OH should be terminal. Looks like E is your answer. All right, next question. You are given an alkene that goes through hydroboration. We are then going to do a tosylation. So obviously in the first step we have to form an alcohol in an anti-Markovnikov fashion, and we have to tosylate it and then treat it with I- to get the major product. So the first step is going to give you your OH in the least substituted position. So your OH should come over here. Now recall that BH3 hydrogen peroxide, that is a syn addition. That means the BH2 and the H are going to come from the same side. What does that mean? That means that if you have a methyl group, and we are going to try to stay as away as possible from the methyl group. So you can perhaps envision that you would either see the formation of maybe methyl on top and both the OH and the H coming from the bottom, or you could see methyl at the bottom, and that would mean that you have a OH coming from the top direction, and the H also in that case will be facing upwards. What does that mean? That means that the methyl and the OH at any given point of time are going to be trans with respect to each other. And so once you have identified that, so let's take a look one more time what my two structures are. You have so far an OH facing downwards, the methyl pointing upwards, and so that would mean that the hydrogen is also downwards. And the other possibility is that if your methyl is downwards, that would mean your OH is pointing upwards, and that would mean your hydrogen is also upwards. That's what you should see. And the next step is that you're tosylating it. So that's a pretty simple, straightforward reaction. All you're going to do is you're going to convert your OH to OTS. So I'm going to just go ahead and make that change right over here. Mechanistically, please refer to the notes that we've gone through over the entire sequence of events of how that happens. But basically, the whole idea is that we are converting the OH into a better leaving group, so that now when it reacts with the I minus, in class we did Br minus, essentially the OTS is going to be willing to leave. Since I minus is a good nucleophile, it's going to follow the SN2 reaction mechanism, which means that it's going to go through a shift rather than an SN1 reaction mechanism, in which case you could have thought that the OTS would first leave, get a carbocation, maybe a hydride shift will take place, give you a more stable carbocation, and then take it from there. But in this case, since I minus is a good leaving group, we are going to go with a simple SN2 reaction. And so when the I minus attacks, the I minus is going to come from a direction opposite of your tosylate. So as tosylate leaves, your I minus and methyl are going to be pointing in the same direction. So one product can be that your methyl is on the solid line, and so is your iodide. Another one would be that methyl is on the dotted line, and so is your iodide. And so C should be your appropriate choice, because the relative stereochemistry between the methyl and the I is going to be the same side. Again, recall, if instead of I minus, if you would have used like a weaker nucleophile like methanol or something, then the reaction will proceed through an SN1 reaction mechanism, because OTS is a good leaving group, and so that will generate a full carbocation that will allow the 1,2 hydride shift to go through, give you a more stable tertiary carbocation, and then the reaction will take place at the same center that is holding the methyl group. So that's different. In this particular case, we are going to follow the SN2 reaction mechanism, and that's going to be your final product. All right, let's take a look at another question. We are carrying out, the question is, choose the structure that is an intermediate in the base catalyzed hydrolysis of acetonitrile into acetamide. This is base catalyzed, that means you have hydroxide, and essentially it's going to attack the carbon. Electrons are going to move. Realize that OH negative is a great nucleophile, so you do not really need the activation of the cyanide as you do in case of the acid catalyzed, because then you use H plus and H2O. So species, first off, species that have a positive charge, you can just omit those out completely. Further, species that are showing you resonance on the other side to give kind of like an alpha substitution type of a pattern, those can be thrown out of the window. Essentially, what is left behind is a situation where you have methyl, OH has attached, double bond, and with a negative charge. That negative is going to pick up the proton and give the carbonyl. But realize that this structure is exactly similar to E, and so that fits the bill. All right, let's talk about further some more reactions, what we have done in the past. All right, the first one has a double bond, it has a proton, and it has methanol. So hopefully you can see that the first step is going to be the protonation of the double bond, so that gives you the more stable carbocation, which is where your nucleophile is going to attack. Your nucleophile here is methanol, so CH3OH. You have your lone pair of electrons that's going to attack, and an ether is going to get generated. It will remain protonated first, and then another methanol molecule or whatever is your solvent that can come in, pick up that proton, and you end up with the ether. All right, let's talk about the next reaction. We have a double bond and we are subjecting that to ozonolysis. We learned in class that anytime you have a C double bond C, the ozone basically cleaves that off right in the middle, and so you are going to end up with a ketone that's going to be connected. The rest of it looks the same, and then we'll try to redraw that. So that's a 1 carbon, 2 carbon, 3 carbon, 4 carbon. So that's a 4 carbon chain on which you have 2 methyls. On the second carbon, you have C double bond O and CH3. On the next carbon over, you have a CHO, and that's your product. All right, let's take a look at the ester. Whenever you have a cyclic ester, that's called a, you got it, it's called a lactone. If it was a amide, you would have called it a lactam. And we are subjecting that to treatment with lithium aluminum hydride. That means that it's going to cleave right in the middle. So you will end up with essentially a primary alcohol, and carbon number 1, 2, 3, and 4. So it's a 4 carbon chain length, 1, 2, 3, and 4, and it will end in an OH as well. So C double bond O, since it's lithium aluminum hydride, you have a lot of hydrides in the reaction mix. The reaction will go through the aldehyde, but it's not going to stop at the aldehyde because of the presence of the additional hydride ions, and you will end up with a diol system in this case, which contains 4 carbons, so you would call it 1,4-butane diol, essentially. All right, let's talk about the next question. The question is, predict the product Z for the following reaction. You're given that you have a secondary amine. You're treating that with a ketone. Recall, primary amines give you imines. Those come from primary amines. And secondary amines gives you enamine. So this is a secondary amine, which is why you expect to get an enamine. And so an enamine is that double bond on which you have a nitrogen. So seems like this is going to be my appropriate choice. But you can, if you wanted to, kind of go through the steps, you can show the activation and then the attack. So your first step will get you the formation of a positive charge over here. Electrons will get attracted, and if you have any of the beta hydrogens, they will get eliminated, and you will end up getting a more stable enamine structure. Okay, the next question is, choose those reactions that can be used to prepare the following ketone. Ketones, how can those be prepared? Looks like there's like a lot of Grignard chemistry going on here. So recall from class, both esters as well as nitriles, they do go through with Grignard reagent. They give you the ketone first, and then ultimately the tertiary alcohol. So in the first case, since they do not say excess, so yes, the first one is going to give you the ketone. The second one is going to give you a ketone as well, because the methyl is going to just add up. Electrons are going to move. You're going to end up with an NH and a CH3. And then the double bond is going to cleave when you do the hydrolysis. So both 1 and 2 are going to give you the product. The next one is an aldehyde. The next one is an aldehyde, and you're treating that with a Grignard reagent. So your R group is going to add up. That will give you a secondary alcohol first. And of course, you will end up getting the ketone if you oxidize it with PCC. So that too will give you the product. So choice E is the appropriate choice. All right, let's take a look at the next one. We are supposed to figure a way out to get this tertiary alcohol. You could go from an ester, and notice in this particular case you're adding two methyl groups, but that would only be possible if you had excess of the CH3 MgBr. So if you just write down CH3 MgBr, if that's what's written, you're not going to get the tertiary alcohol, but rather the reaction would stop as a ketone. So in this particular case, the first one, of course, that's going to deliver the phenyl group right over here. So that will give you the tertiary alcohol. So 2 definitely is going to give you the product. Likewise, if you look at the third one, you already have the methyl and you already have the phenyl. So this methyl and this phenyl are there. The third one is what you want to put in there. So that can be added via the Grignard reaction. So 3 also is likely. So 2 and 3, both of those are going to give you the product. The first one is only going to give you if you see excess. If not, don't worry about it. And so choice C is the most appropriate choice, the way this question is worded. But if you do see excess, then of course 1, 2, and 3, all 3 of them are going to give you the desired product. Okay, the question is that you're given several structures. Which of the above molecules is a hemiacetal? So recall, a hemiacetal means that there should be an OR linkage on one side. So you have a carbon, there should be an OR linkage on one side and an OH link on the other side. That's what is a hemiacetal. This is just an alpha beta unsaturated ketone. That's just an aldol. This is an acetal. And this absolutely is a hemiacetal. That is just an imine. All right, well, that was simple enough. Choice D. Each of the following compounds is chiral. A sample of a single enantiomer of each compound is dissolved in ethanol and exposed to a catalytic amount of sulfuric acid. 4 of the compounds are observed to racemize. 1 does not. Which compound would not racemize in presence of an acid? This truly is a test of your ability to be able to identify acids over something which is not as acidic. So chapter 23 is what it revolves around. So recall from class that when you have a ketone, that's going to essentially allow the enolization or formation of the enol using the alpha hydrogens, and that will have a pKa of close to about 20. Same will be the case over here. Of course, if you have two electron withdrawing groups, the pKa is going to drop significantly, and you're going to see a number close to about maybe 11 ish or so, 11 to 12. And if you have a nitro group, that's even more as compared to your ketones and ketoesters. So we are looking around 10 or so. Nitriles, on the other hand, they are a little bit more basic, you can say, or the pKa is higher. The pKa of CN, C triple bond N, is 25 or so, and so it's going to be difficult to remove that proton. And we are saying that we have to remove the proton because for the racemization to take place, you have to lose that proton, you have to get it into the enol version. So now that you have a double bond, when you bring in, the attack can occur from top or bottom. So you have to get to an sp2 type of a situation. So D should be your most appropriate choice. Okay, next question. Predict the product of the following reaction sequence. So you are given an alkyl group on the benzene, which we are subjecting to a Friedel-Crafts acylation. So notice that alkyl groups are ortho and para directing in nature, so that means that your incoming group is going to go either at this position or this position. Further, we are going to carry out a nitration, and eventually we are going to subject that to Clemmensen reduction. So let's take a look how that's going to go. So we have our isobutyl group, and your possibility for your incoming group would have been at the ortho position or the para, and of course the para position is going to be more stable for steric reasons. So that's what you're going to end up with. Now you're doing a nitration. That means with respect to your ketone, you're going to say that it's going to be a meta director. With respect to your R group, it's going to be ortho director. The para position already has been taken. So you're going to end up with a final product where you have the aryl ring, the sec-butyl group already intact. You're going to get a C double bond O with the ethyl and the nitro. And now we are going to subject that to the Clemmensen reduction, and that would mean, and you could have done a hydrogenation, you could have done an H2 palladium here as well, and then recall that different amounts of pressure are going to have a different kind of product. We talked about that in class. The Clemmensen reduction is going to be specific for the ketone to give you the corresponding alkane. It's not going to touch your nitro group. So the product in which you have the nitro, ortho with respect to the sec-butyl, and meta with respect to the product is going to be your final product, and that should be product A. So you will end up with, let me draw the product for you, the sec-butyl, the nitro, and the propyl. All right, next question is predict the major product of the following reaction. You have benzene, you're subjecting that to isobutyl chloride and AlCl3. So your carbocation is first going to be a primary center that is going to go through a shift, give you the more stable tertiary center, and that's what you should add up. So choice D, or rather go through substitution, electrophilic aromatic substitution. So choice D is your most appropriate answer. Okay, this is a pretty straightforward question. You're trying to read a given alkene with NBS, NBS. And what's so fancy about NBS? That it either attacks a benzylic or an allylic position. So you have two allylic sites over here. One is over here, the other is over here. So the question is, where would that bromine end up being? Notice that two of my products are showing vinylic center, so those are not true. One of them shows that it's going to go at the primary center, so that's not true. And if you think about the mechanism, since this does go through the free radical mechanism, you are going to generate a free radical that looks like this, which is going to be resonance stabilized, by the way. So you would end up with a double bond and a secondary free radical, or you would have the free radical, which is tertiary and allylic. So this is tertiary and allylic, and this is secondary and allylic. Recall what we talked about in Organic Chemistry 1. Tertiary allylic free radical is more stable as compared to the secondary free radical, and the bromine kind of seeks the most stable one before it actually goes on for the reaction. So choice A should be your most appropriate choice in this case. All right, let's talk about two final questions. The question is, consider the following compound. And so you're given 5 different compounds and you're asked which one would be classified as aromatic. Hopefully you can see that the first one itself, it's an sp3 center, so non-planar. That's not going to cut it. Choice D, again, you have planar structure, so D is not aromatic, and so E is not for the same reason. E is not aromatic either. If you think about C, that's going to be anti-aromatic because you have now 8 electrons. And if you think about the tropylium ion, everything is sp2, and you do have 6 electrons, which does follow Huckel's rule. So choice B is going to be the most appropriate answer to this one. All right, predict the product of the following reaction sequence. You're given toluene, which is subjected to Friedel-Crafts reaction, further it with bromination, and then hydrazine and KOH, which is going to reduce the ketone. So let's take a look at what we are going to get out of this. So we have the COCl that is going to give you the para product, and the further bromination is going to give you the Br at the meta position, because now you have a ketone, and that ketone is meta-directing in nature. When you reduce it with hydrazine and KOH, that's going to convert this acyl group into the propyl group, and so your product should look like methyl. Ortho with respect to that should be bromo, and the relationship between bromo and the propyl should be meta with respect to each other. So looks like we would have choice A as the final answer. So think about, sequence of reactions, what can happen. So having the reaction summaries and what converts what to what is an ideal way to prep up for yourself. Of course, in addition, you're going to think about all previous quizzes, previous exams, including exam 4. All of those are up for grabs. You should know how to convert. Maybe you would have seen that as a box problem, and now you will see that as one of the choices for a certain reaction. So you should know the conversions. That's an important part.